now. Okay, is this set linearly independent? Obviously, we've shown that it isn't. Well, we have 1, 1, 1 here. This is a multiple of 1, 1, 1. I'm going to say no. Set 4, 4, 4 equals the set, the vector 4, 4, 4 equals the vector 1, 2, 3 plus the vector 3, 2, 1. So if we call these V1, V2, and V3, V3 equals V2 plus V1. Now, geometrically, this means that we have vectors V1 and V2. And as I've illustrated before, you can go out along V1 if you want to construct any vector in the span of V1 and V2. Now, what's it mean for this vector to be in the span of V1 and V2? Okay, here's a vector V in the span of V1 and V2. This means that we can go some distance. Let's say we've got V1 here. And that was a bad place to label it. V1 here, and let's say V2 here. Is it going to be a bad illustration? Well, we're going to do it anyhow. Okay, so here's V1, here's V2. If we go off in the direction of V2 from the end of V1, we don't quite get to the tip of V. If we come out just a little further along V1, we get to a point. So here's V1. Here's some constant times V1. So we're going to call this vector here C1, V1. Now, if we go in the direction of V2, we're going to get to the tip of V1. So here's a vector parallel to V2, so that it's a multiple of V2. Here's a C2, V2 that gets us to the vector V. Okay? Now, having V1 in this set doesn't help us get anywhere else. Now notice that these vectors, V1 and V2, are in three-dimensional space. So I'm just looking at V1 and V2 from some perspective in three-dimensional space here. And I'm not going to be able to, and this is a plane, okay? The plane is defined by V1 and V2, and we've seen that, okay? V1's this way and V2's this way, then you have a plane here. And this vector V has to be in the plane in order to get to it by a multiple of V1 and a multiple of V2. This vector doesn't add anything to where we can go in three-dimensional space with these two vectors. Any place we can get with these two vectors, we could get with a combination of these two plus this one, because this one is also in the plane. Okay, so I can make a statement that we can form any vector in the span of V1 and V2 which is the plane defined by V1 and V2 with a linear combination of V1 and V2. Again, wherever this vector ends, we start same initial point because we're always starting at the origin. And we move along V1 until we get to the point where our direction to V2 is the same as our direction to V is the same as the direction of V2. Okay, the set is not linearly independent. This set is not linearly independent. Since V3 is also a linear combination of V1 and V2, so it's also in the plane of these two vectors. And I'll just say that V3 doesn't get us out of the plane of V1 and V2. Okay. Well, we can determine that all this is the case if we take the matrix and row reduce it. So if we do the first step of row reduction, remember we can add -2 times this row to this row. Get 0, -4, -8. And then we can add -3 times the first row to the second, to the third. And we're going to get 0, -8, not -8. 3 times that is 9. Yeah, it is. 3 times that. Yeah, okay. We do get -16 somehow. Wasn't seeing the -16. Okay, we get this. Now, geometrically, I'm going to do something different. Same thing, essentially. But I'm going to wipe this out. We've seen calculation I was about to do here, but I want to talk about this in terms of the three vectors. I'm going to do something that maybe isn't totally motivated, but is totally related to where we're going with this, to row and column space. Okay. I'm going to do the transpose of this so that now my vectors 1, 2, 3, 3, 2, 1, and 4, 4, 4 are my row vectors. So that when I do the first step of the row reduction, I'll add -3 times the first row to the second. So my first row is going to stay the same. My second row is going to become 0 and -3 times 2 and so forth. That's going to give me -4. And -3 times the 1 is, or -3 times 3 is -9. And we're going to get 0, -4, -8, same as we got before. And then subtracting 4 times this from this, 4 times 2 is, of course, we've got to get 0 here. 4 times 2 is -8. We add that to 4, we get -4. -4 times 3 is -12. Add this to 4, we get -8. Now that looks familiar, but what we were going to get before we did the transpose had -8, -16 here. Okay, well, that's just the arithmetic. What's it mean? This vector is V1, this vector is V2, this vector is V3. So what we've done here is we've taken the matrix that we can write as V1, V2, V3. And we've added, well, what we've got is V1. Here we added -3 times V1 to V2. So this is -3 V1 plus V2. And then we have -4 V1 plus V3. These vectors are all linear combinations of these vectors. Matter of fact, geometrically, if V1 is here and V2 is not really the way they would be, but let's say here's V2 and here is V3. Now what we've got is V1 okay, this picture becomes this picture. We've got V1. And then we have -3 times V1, which would be 3 times as long as this back in this direction, plus V2. So maybe it's like here. So we got -3 V1 plus V2. This being a linear combination of V1 and V2 is still in the plane of V1 and V2. And then this vector, -4 V1 plus V3. Okay, I'm not putting it exactly where it would be, but it's going to be back this way a little bit, but this is -4 V1 plus V3. Okay. Now this vector is still in the plane of V1 and V2. So this one is in the plane of V1 and V2. In general, remember, these are in 3 dimensions. They don't necessarily have to be in the same plane, but this one might not be in the plane of V1 and V2. Now, since these vectors came out the same, because that's what these rows are, this vector and this vector is this vector is this. Now let's pretend that we hadn't seen that this and this are the same, or let's pretend that, instead of being 4, 4, 4, maybe this is 2, 2, 2, so that it's not as obvious that this is a multiple of this. We go one more step in the reduction. And here's the payoff. We get 1, 2, 3, 0, -4, -8, 0, 0, 0. Because of course, we're just going to add the negative of this row to this row. Okay. And I didn't leave myself room to write it. Bad planning on my part. So I'm gonna write it here. It's not the best, but maybe it is. V1. What I've got now in this row is the -4 V1 V3 that I had here. And then minus -3 V1 plus V2, which of course equals V1 -3 V1 plus V2 and -4 V1 plus V3 minus this. Well, on V1, we're going to have -4 V1 minus -3 V1. That's -4 V1 plus 3 V1. So that's -V1. And then we have just plain old minus V2 because we don't have any V2s here. We have this. And we see from this row of zeros -V1 minus V2 plus V3 is the 0 vector. So this set is not linearly independent. Well, the fact that this set is not linearly independent tells us that this vector is in the plane of these two. In fact, this vector is going to equal V3 plus V2, and it doesn't look that way. But remember, this is a schematic diagram. It's not supposed to really represent the vectors. Okay, so we conclude that this vector here is in fact in the plane of V1 and V2. That all three vectors are in the same plane. Okay, well, those are the details. But let's write this result out. I'm missing something. Oh yeah, here it is. Let's see if I can get it out of here. I'm handling these boards a little bit differently today because I don't want to write up this high on the board. Among other things, it can be hard to read. And let me, I think we're okay there. Yeah. The other thing is it kind of hurt my shoulder a little bit reaching up there the other day. Done something. Be okay in a couple of days, but I don't want to push it. And there's some advantages to having boards this way. Okay, so anyhow, so what we've seen is okay, this reduces to this, so the columns of the original matrix, which became the rows of this matrix, were the rows of the transpose matrix, which is what we reduced over here. Are not linearly independent. Okay, because row reduction I'll say constitutes adding multiples of row vectors, and I'm not going to be any more specific than that, although it could be. I think you should get the idea. This constitutes adding multiples of your row vectors which doesn't change their span. A row of zeros then tells us it's some linear combination of the original rows gives us the zero vector. And this is essentially, these statements are essentially a proof that if you, well, that the span of the vectors you get here is the same as the span of the vectors you started with. Now there's a little bit in between there, but you can kind of keep this. So the span of the rows of the reduced matrix is the same as the span of the original matrix. In the case of the example, well, the span of this matrix is just a plane. Span of these rows is just a plane in R3. We're in R3 because these vectors all have 3 components. We could even take this further and do a reduced, this is your row echelon form. We could do the reduced row echelon form by adding a multiple of this row to this row to get, and then doing a little arithmetic. Well, divide this row by 4, or by -4, we get a 1, 2 here. And then we subtract 3 times that from this, we're going to get a 0 here, a 1 here. Then we're going to get something else up here. Okay, well, we're not going to do that with this matrix, although we easily could. It turns out then, and here's the big deal, the rows of the reduced echelon matrix, and you should understand what I mean by reduced echelon matrix. I haven't used the term, I've just used completely reduced. But you see this term in your homework and in your text. So if you don't understand what that means, I'll explain it quickly, but then refer to your text. An echelon form is where I'm not going to go into the echelon is something that comes from, I think originally a military formation where every row, if a row is behind another, then it's got to be shorter than the other on one end. So it's like, here's a row of soldiers. This row doesn't have anybody here. So this row is shorter than this row on the left. And this row is clearly shorter than any of these rows because nobody's here. But if we had a soldier here, then this row would consist just of a soldier here, and it would be shorter than the row above it. Okay, I'm gonna offer that idea for echelon, but it's what we've achieved by row reduction. If you complete it, do a reduced echelon form, then you have a leading one in every row. So it's like you have a leading one is like you have the leader of that row who keeps everybody else in line. And whoever's here is responsible for the whole row being empty to his left and so forth. Okay, so the rows of the reduced echelon form are a basis for the span of the original rows. So the original rows of the transpose matrix, which we have here, are the vectors that we started with here. So now we have, well, here's a basis. Okay, these two vectors form a basis for that span, for the vectors in that plane. Okay, a set of two vectors that span the plane. If we reduce it further, we get even simpler vectors that span the plane. So to get the span of a set of vectors, we put them in a rows. Well, we put them in the rows. Okay, we transpose this so that our vectors are in rows, and we reduce the matrix, and we can further reduce it. Okay, and as soon as we get a row of zeros, or get this thing in echelon form, we're going to maybe have some rows of zeros, maybe not. Whatever we end up with, as soon as this thing is completely down into echelon form, we have a basis for the span, the space span by the three vectors. That's really very important, which is why I've taken like a half hour to go over an example and try to establish this whole picture. Okay, now with that, we're going to make a few definitions. Oh, that's not going to work. Okay, hang on a minute. I've got to flip something over. I guess it's got to be this one. Fortunately, there's something to keep that thing from falling over. No, it isn't. Okay. Maybe overlap a little bit here. Here, eventually I'll get used to the things that can go wrong. Okay. Now I can only go over to about here. And I prefer to be able to go over to the end of the board so I don't lose track of what I'm doing. That's not going to fall. That's going to be okay. I'm going to put this here, just to make sure that this one doesn't fall off. Okay. To make it less likely, it's not, nothing's going to be sure. Okay, we're better off there. Okay, so a couple definitions. Whoops, wrong color. Row space of a matrix and let's make the matrix V1 through Vn. We don't have to confine ourselves to columns of 3. We could have columns of 48, columns of 78 million. Okay, but some V1 through Vn is the span of the set. V1 through Vn. The dimension of the row space is the number of non-zero rows in reduced echelon form. Okay, and it doesn't have to be reduced, but we like the reduced echelon form because it generally gives us simpler vectors. And do we have all that? Yeah, it looks like we have it. Okay. Column space of the matrix V1 through Vn, which is written this way, and we don't have commas. Okay, in other words, V1 through Vn are in columns here. In this notation, they're in rows. Okay, column space of this matrix is a number of non-zero rows in optimally reduced but any echelon form of the transpose of this matrix. Because when you transpose this matrix, the columns become the rows, and this is then the row space of these vectors. So I'll say the transpose of this is the, well, be this, okay? So again, you have column vectors. You take the transpose, those column vectors become your row vectors. And what we just said about row vectors is that the dimension of the space is number of non-zero rows in the reduced echelon form. And if you understand what's been done here, that's the same as the number of non-zero columns in this vector. So it's totally equivalent. There's a total equivalence between what you do here and what you do here. And you want to sort that out a little bit. Okay. And then in either case, and I think I stated it already, we come back to the statement I made here. You can't read the whole thing, where I said the rows of the reduced echelon form are basis for the span of the original rows. Okay. This is something we established, at least in terms of the example, and it can be easily proven if you understand the details of what was done with the example. So you reduce a matrix to echelon form, and you get a basis for the rows, for the row vectors, for the span of the row vectors, for the set of row vectors. Okay, so the rank of a matrix is just the number of rows you get. I'm just saying the number of rows when reduced because I don't want to put all the words up here for sake of time and space. Board space, not vector space. Rank of a matrix is a number of non-zero rows when you reduce the matrix. Okay, we know how to reduce matrices. Hopefully that's an automatic, simple process. And hopefully when you're reducing the matrix, now you can think of the fact that essentially you're just adding multiples of your row vectors to one another. And of course, you're multiplying rows by constants and so forth. Okay. And none of that changes the span of the set. Okay. So that's the rank of a matrix. Rank of a transpose of a matrix is equal to the rank of the matrix. Okay, because all you're doing is you're making the columns into rows. And if you understand how this works out, it maybe isn't totally obvious, but it's easily proven, and you'll see that result. And I don't want to go through the details of that for sake of time. Okay, so the rank of the transpose is the rank of the matrix. And as a result, the dimension of the row space is equal to the dimension of the column space. Going to do another example to illustrate an important aspect of this. Now, in most of what we've done, our vectors are our matrices, and in the examples we've done so far, our matrices have been square matrices. But none of this is confined to square matrices. Now, square matrices are really important because those are the ones you try to invert and so forth. to solve a matrix equation, but your matrix equations don't always represent, let's say, systems of n variables, n equations and n variables. So let's let A equal the matrix. I'm going to stick with our 1, 2, 3. Then I'm going to put a 5 here. And any numbers I want to put here. Okay, so here's our matrix. Well, this matrix reduces, as we've seen, at least to 1, 2, 3. And we could put the 5 here. Okay, and then 0, -4, -8, and some number here that we could easily calculate, and 0, 0, 0, and some other number here that we could easily calculate. Okay, so this reduces to this. And I'm reconsidering what I just did, but I'm not going to. Okay, so usually, except for very specific choice of, say, the numbers, well, the numbers you have here, this whole process is not going to give you a 0. Okay. Now, what I'm going to do is, instead of having specific numbers here, I'm going to represent whatever numbers are here by asterisks, and whatever numbers are here by double asterisks, except for this one, which at this point is going to be the same. So you understand that this matrix will reduce to a matrix here, where depending on what numbers go here, we get different numbers here. And if we take this one step further, of course, well, I'm not going to do that. Okay, so and I'm actually going to put a triple asterisk here because this one is what's important. If this triple asterisk here is not 0, which it will usually be if you just randomly choose numbers here, okay? You'd have to choose numbers very carefully to get this thing to match up with these in such a way that you get a 0 here. Could happen, but not. If triple asterisk is 0, then the rank of A is 3. Okay, then now A transpose okay, here it is. And of course, we know automatically that whatever 3 rows we have here, when we end up reducing this, because this represents 4 equations in three unknowns, we're going to end up with a row of zeros. So this is going to reduce down to, I'm not going to be specific. I need a different symbol. Okay, it reduces down to matrix. It's going to have a row of zeros. Okay, any matrix you have here has got to have at least one row of zeros, might have more than one. I'm just going to assert that, and actually, what I just said isn't correct. We're going to have two rows of zeros here. Now I'm just going to assert this. Okay, but this is guaranteed if we understand that the rank of A and the rank of A transpose are the same. Okay, since the rank of A equals the rank of A transpose, they're the same. And also, now you can test this yourself, okay? You put any three numbers you like here and reduce the matrix. And if you just randomly select those numbers, it's almost impossible that this, oh man, I did something wrong. Okay. Rank of A is 3. So this is a row of non-zero elements. And what I said is true. But we talk about reducing this to echelon form. The echelon form here would consist of a 0 here, 2 zeros here, and then a row of zeros. So I wrote that down carelessly. Go back again. Okay, so we reduce this matrix and we find that we're going to get this form where none of the three rows is all zeros, usually. So assuming that none of three rows are all zeros, that means this thing doesn't come out to 0. We get the rank of A has to be 3. If we reduce the transpose, it's got to give us a rank of a matrix of rank 3, since this is always the same. You'll see that proven in your book. You should try to understand that proof. In that case, this matrix has to reduce down to this form. And you can verify this, as I started to say, by just picking any three numbers here, reducing it. If you don't get a 0 here, then you've got a matrix of rank 3. So now when you do the transpose and reduce it, it's guaranteed that you're going to get this form. You're going to get exactly one row of zeros and 2 rows in echelon form, none of which are 0. Okay, 3 non-zero rows, because the rank of A has to equal the rank of A transpose. Now, once you have that, you establish that the dimension of the row space equals the dimension of column space. Why does this say the same as this? Well, it's because the rank of A is the dimension of the row space of A. When you do the transpose, the row space of A becomes the column space of A transpose. So I didn't say that exactly right, but think about it. Okay. Now, again, this is a much bigger deal than it might seem right now. And again, doesn't apply just to square matrices. Another thing is, if A is has M columns, the rank of A can't be bigger than M because, of course, the dimension of your row space can't be bigger than the number of rows that you start with. So the rank of A has to be less or equal to M. Having trouble with words, and of course, I guess you're getting used to that. Thinking ahead. What I wrote was true, but we want to stay in terms of rows. Okay, the rank of A is the dimension of the row space. If we have M rows, rank of A is less or equal to M. No matter how long the columns. And then if A has n columns, rank of A is less than or equal to M, no matter how many rows you've got. Okay, now we've got to get to one big deal result. As soon as I figure out how to manipulate these boards. Okay, I can't do any more with this. Kind of want to keep it available. And I can take this board and invert it. Put this board over here. And flip it. Just a little more space there. Yeah, that'll be okay. And I'm finding I want these boards to be just a little cleaner, because when we have smudges, for some reason, I don't see it when I look at my screen here, which has shown me the same thing you should be seeing. But in the videos, the little smudges tend to obscure the writing. Might be something about the camera. It's an excellent camera. Okay, so now, big deal. The matrix equation, come back to my 1, 2, 3, 3, 2, 1, 4, 4, 4 matrix. Okay, this equation is of the familiar form, and I sincerely hope it's the very familiar form to you now, that of the form AX equals B. A isn't invertible. And it should be clear why not. It's not invertible because it's impossible to reduce the augmented matrix A with the identity to identity A inverse, because A doesn't reduce to the identity. Okay. Now, A doesn't reduce to the identity is equivalent to saying the determinant of A is not 0. You take that determinant, it's not going to be 0, but we don't have to do that right now. We've already reduced this matrix and found that it has a row of zeros. So it doesn't reduce to the identity. So we can just say this. That's totally equivalent to saying that the determinant is 0. The augmented matrix now, wait a minute. 1, 2, 3, 3, 2. Yeah. Okay. This is the augmented matrix we would use to solve this equation. And of course, we know what system of equations we're solving here. You know, it's C1 plus 3C2 plus 4C3 equals B1. 2C1 plus 2C2 plus 4C3 equals B2, and so forth. Okay, we need to see all that. When we look at this, we need to understand all that kind of automatically and immediately. So it should be obvious then that this reduces to I'm going to reduce it all the way down. I'm going to use a double star for this. This number can't equal 0. This is false unless double star happens to be 0, and double star isn't going to be 0 unless you have exactly the right B1, B2, and B3. So this double star is not 0. Unless you have just the right B1, B2, and B3. In other words, this system says C1 plus some multiple of C2 equals some other number, C3, sorry. And C2 plus some other multiple of C3 equals some number. And some combination of B1, B2, and B3 is 0. Whatever combination you get when you reduce this. Now we can reduce it and get it specific. Okay, well, let this combination be and I just thought of it. For example, we don't get it here. You can reduce this, you can do all this, and you can find out what this combination is. In other words, when you add -2 times this to this, you're going to get a B2 minus 2B1. When you add 3 times this row to this, you're going to get a B3 minus 3B1. And then when you take 1/4 of that, -1/4 of that, you're going to get 0. So you could write that out. I could write it out, but I'd probably do something wrong in my head, so I'm not going to. For example, though, we might get I'm not going to get this. But we might get this. Okay. It's not what we're going to get for this matrix, but for some other matrix, it certainly would be possible. I'll say any B1, B2, B3 satisfying this equation just looking for space to write the words. If B1, B2, and B3 happen to satisfy whatever equation we get here, then you can find C1 and C2 and C3 such that this works. So I'll say any B1, B2 satisfying this equation yields a solution to the original system. And I wrote too low on the board, so I'll raise that up, okay? In other words, the original system represented by these matrices. And well, that's an observation. In this case, and I'm just looking for board space. Okay, I'm going to just do that here. Okay. This matrix product is equivalent to this, which we know then reduces to this. We know that this matrix reduces to this form because we know we get a row of zeros here. And in this case, we get a -4, 4 in this row. We can then divide by -4 and then add -3 times what we get to the row that we had here and get the 0 here. We can do all that. That's very straightforward. And we also know that no matter what row operations we use, in this column, we're always going to be adding 0 to 0. And if you don't understand that, go ahead and reduce this matrix. So we end up with this matrix that represents these equations. C3 is a free variable. As usual, we're going to let C3 equal T. Okay, so I should have maybe said that. And C2 is some multiple of T. So for example, if C2 equals 2T, and you can work out what it would be for this matrix. You can work out these numbers, it's easy. If C2 equals 2T and C1 equals 5T, then C1, C2, C3 equals 2T, 5T, and C3 was T, equals this. And that equals the vector 2, 5, 1 times T. So 2, 5, 1, any multiple of 2, 5, 1 is a solution to this equation. Now this is your homogeneous equation. And this would be an example of a solution to the homogeneous equation. And this is a one-dimensional subspace spanned by just the vector 2, 5, 1. Okay. Sorry about the board management here, but so if this matrix equation has solution, what was it, 2, 5, 1, T equals 0. And the solution is the span of vector 2, 5, 1, a one-dimensional subspace of, we'll say, R3. That'll be done in just a minute. I'm going to make a big point here. Okay. Note, okay. This subspace is the null space of the vector A. Null space because it's a set of vectors that get nulled, okay, that when multiplied by A, give you the zero vectors, the set of vectors that collapse to zero. That's a set of vectors that A collapses to zero. Now, big deal. Rank of A plus a dimension of the null space equals 2 plus 1. That's the dimension of your whole space, R3. In general, rank of space plus the nullity of A, and the nullity is the dimension of the null space. Is equal to the number of rows of A. Now you can also talk about what happens to the column space. Okay, now quickly, I'm going to somewhat modify the assignment, and I'll get you an email on that. This is really a big section. And I'm going to not give you any assignment for next week, no assignment for next week, so that we can prepare as best we can for the midterm. The midterm's officially due a week from tomorrow, next Friday, but I'll accept it up to the first day after we come back from spring break. So if you want to give yourself a little more time, maybe use the coming weekend, one of the 2 weekends in spring break, or, piece away out a little over spring break. And I really think you ought to try your best to actually take a break over spring break so you can come back fresh. But I'm going to give you the flexibility to do that, and I'll detail that. I haven't completely worked out a strategy for the midterm and for the rest of the semester, but I'll be working on that. I get my second COVID vaccination this afternoon. I don't expect to have much of a reaction, but we'll see what that does to my ability to do this quickly. But I'm hoping to be able to give you a better idea of that tomorrow. Okay, so that's where we are. Sorry for holding you over, and I'll have to apologize to my next class because we're going to start that a little late, but it's kind of a big deal section. Hopefully, I gave you some examples by which you can understand what you read in the section, and I'll give you a little more guidance on exactly what you need to be looking at, and we'll go from there. Okay. If you got a big question, go ahead and ask me, but I'm going to have to close this out in just a minute. Chris, you doing okay? Okay, well, email me if you have a question, and I'm going to close out now.